Hello everyone. I'm Liuqing Zhang from Baidu, responsible for Baidu's monitoring system. Today, my talk is automatic traffic scheduling for internet connectivity failures. There are three parts in my talk. First of all, I will introduce Baidu's network architecture and how internet connectivity failures impact the user experience on our service. Internet connectivity failures impact the user's experience on, In order to improve user experience, we need to detect the failures and handle them. Then I will introduce how to do automatic internet and connectivity failures detection. Last, I will talk about automatic traffic scheduling to handle these network failures. Okay, let's start. There are two main approaches to internet connectivity failures. One is to case the dynamic routing BGP network provided by the ISP to connect the data center. BGP can automatically detect failures in network links and automatically route requests to healthy links. Most internet connectivity failures can be resolved automatically. However, the price of the BGP network is expensive, which adds a lot of cost to companies. Another approach is based on the traditional static routing network, using DNS for traffic scheduling to handle network failures. This method is much cheaper than using a BGP network. Most of Baidu's data centers currently use static routing. So today we introduce how to handle internet connectivity failures based on DNS. Let's take a look at the process of users visiting Baidu. In order to make users in different provinces get the best user experience, reduce network delays, we use DNS to schedule user requests from different provinces to the nearest data center. And so in the figure, users in North China will be scheduled to Baidu's North data center. Users in South China will be dispatched to data centers in the south. Users' requests will go through the local ISP network, ISP backbone network, and finally reach the POP of the Baidu's data center, requesting Baidu's backend service. Failures can happen on all these three segments in the path. They can cause different scopes of impact and requires different scheduling methods. The first is the data center POP failure. POP, point of presence, is a network link for connecting data center and ISP when the POP network failures or requests to the data center fail. In this case, we need to schedule users' requests to other data centers with healthy POP links. The method is to adjust the DNS to replace the IP of the faulty data center by the IP of a healthy data center. The second type is the ISP backbone network failure. This failure can break the connectivity between users in one area and our data centers in another area. For example, users in Central China will normally visit the Baidu's East China data center. When the ISP backbone network links between Central China and East China have failures, we need to schedule the user's requests from Central China to North China or the South China. In this way, users can access our service normally. The third type is the local ISP network failure and the user side. In this case, the link between the local network of a province and the ISP backbone network has some failures. Users from the province and ISP cannot access Baidu's data center in the same ISP. For example, the failures of the network of China Unicom's Beijing local ISP will cause its users to lose access to Baidu's data center in China Unicom. Interestingly, we found that these users can access Baidu's data center in other ISPs, such as China Mobile and China Telecom. The reason is that although the connection between the Beijing local ISP and China Unicom's backbone network has failed, the links between different ISPs in this province are still healthy. Therefore, we can replace the data center IP resolved for Beijing Unicom users with the IP of Baidu's data center of China Mobile or China Telecom. Okay, let's look at the impact of these network failures. The data center POP network failures occurring 12 to 20 times a month, with an average duration for more than 1 hour. The ISP backbone network failures occurs infrequently. It happens 0 or 1 time per month, but its average duration is more than 2 hours. The duration of local ISP network failures are relatively short, 16 minutes on average, but the frequency is very high, with more than 20 occurrences per month. Okay, taken together, we will encounter more than 30 connectivity failures each month. Based on manual operation, the recovery duration will be more than 30 minutes. This will bring a lot of user experience damage. At the same time, based on this slow manual operation speed, some of the failures cannot be covered at all. For example, most local ISP network failures are restored before the manual operations complete. Therefore, we need automatic network failure detection and automatic traffic scheduling to achieve automatic operation of internet connectivity failures. Okay, first of all, let's look at how to automatically detect these failures and identify what type of failure is. We built the Falcon network monitoring system. Basically, Falcon installs a set of probes on the user side. The probes will send requests to our data center POP and then submit probing results to Falcon. Falcon detects failures based on the probing results and generates alarms accordingly. The key problem is the probes coverage. Based on the previous discussion, if we want to discover the failures of local SP network, we need to install probes in all provinces and SPs. China has more than 30 provinces and more than 10 SPs, so at least 300 probes are required to meet the demand. Of course, we cannot deploy only one probe for each province and SP. To ensure data quality, we need much more probes. Okay, we eventually choose to use Baidu's peer-to-peer CDN service to deploy our programs. P2P CDN recruits user devices' idle resources to store Baidu's web contents in order to accelerate accesses to these web contents. We deploy more than 3,000 probes in P2P CDN. The probes are scattered enough to cover all provinces and major ISPs in China. This can meet the needs of failure detection. And compared to buying external virtual machines to host probes, the price is much cheaper. Then we introduce our detection method. One of our detection tasks is to send HTTP requests from a number of probes in a province to a data center to detect whether the connectivity between this province and the data center is normal. Although P2P CDN solves the coverage problem, we found a problem that the P2P CDN probe itself is not very stable. Many requests failed because of the problem of related probe itself. And so in the figure, we select 5 probes in the province. The 5 probes send HTTP requests to the data center every 10 seconds. In the figure, each dot is the detection result corresponding to one result. A red dot indicates that the probe request failed or timeout. A blue dot indicates that the request is normal. We determine connectivity status by summarizing the probing results in 1 minute, because we have 5 probes and each probe sends requests every 10 seconds. We have 30 detection results in 1 minute. When the ratio of abnormal detection results exceeds a threshold, we conclude the link is abnormal. For example, we set threshold to 20%. Let's look at the effect of judgments. Okay, in situation 1, although the abnormal ratio has reached 20%, the abnormal detection results concentrate in probe 1. In this case, it is more likely that probe 1 itself fails and the link is healthy. In situation 2, the abnormal detection results scattered on multiple probes. In this case, the link is more likely to be abnormal. Therefore, we implemented a failure detection filter algorithm when the anomalies concentrate on 2 or less probes. We will decide the probes are abnormal and the link is healthy. Based on the probing results, we can get the abnormal ratio from each province to each data center. As mentioned at the beginning, we need to distinguish different types of failures to execute different traffic scheduling methods. So we need to analyze the type of failures based on the abnormal ratio data from provinces to data centers. we use multi-dimensional aggregation to achieve this goal. The data is aggregated into 3 dimensions: province, area, and data center. The type of failures can be determined by the following judgment method. When failures are concentrated in one province, we thought it was a local SP network failure. When failures are concentrated in multiple provinces in one area, we believe that the SP backbone network failure was occurred. When failures are scattered in all provinces but are concentrated in a single data center, it can be determined as a data center network failure. In this way, we can automatically detect the type of internet connectivity failures. Okay, we have introduced the type of internet connectivity failures and the automatic detection method. Next, we look at how to implement automatic traffic scheduling to solve network failures. In the DNS traffic scheduling operations, we need to consider 2 factors. The first is network connectivity. We have just introduced our Falcon network monitoring system to detect internet connectivity failures. So we need to implement different scheduling methods for each type of failures so that the user's request can correctly access Baidu's data center. Second, we also need to consider the bandwidth capacity of each data center's POP. We should not overload the bandwidth capacity of a data center by traffic scheduling. Therefore, we designed GTC, a global traffic control system. According to real-time network connectivity status and bandwidth usage, GTC generates the best DNS configuration to execute on DNS service. Here is an example about how GTC handles a complex situation. As shown in the figure, the POP network of data center 1 fields. We need to schedule the requests to data center 1 to other healthy data centers. The traffic to data center 1 comes from users in province A and province B. Both province A and B generates 30 GB traffic. Currently, we have 2 healthy data centers, data center 2 and 3. Then their bandwidth capacity are both 100 GB, and their current request occupies 60 GB. So each of the data centers has only 40 GB idle bandwidth. If we schedule the traffic from both province A and province B to one of the healthy data centers, the selected data center will be overloaded. So GTC needs to consider the bandwidth capacity to avoid this situation. The best scheduling plan is to dispatch one province to one data center. For example, dispatch province A to data center 2 and dispatch province B to data center 3. Based on the above method, GTC successfully avoids overloading the destination data center's POP network. But it still misses a problem. That is, the capacity of backend service can be overloaded. In our previous example, when the POP network of data center 1 is down, GTC schedules requests from province A to data center 2. The 30 GB requests will bring 1,000 QPS to the backend service in data center 2. The original request to data center 2 is 2,000 QPS, and the capacity of backend service is 2,500 QPS. When the traffic of province A comes in, the total incoming requests become 3,000 QPS, exceeding its capacity. So the backend service is overloaded. How to solve this problem? We find that Baidu's internal network are generally independent to the internet failures. With an internet failure happens, the internal network is usually normal, and the communications between data centers and are still smooth. The data center's communication is still smooth. Therefore, we consider adding a layer to Baidu's internal network to implement traffic rebalancing. We built BFE, a layer 7 load balancer, to schedule requests to a busy service in one data center to a less busy service in another data center. In our example, one BFE system in data center 2 observes 3,000 QPS requests. It looks up the corresponding service capacity dates in a configuration database and finds out the capacity is 2,500 QPS, less than the incoming traffic. So it scheduled 500 QPS to the service in data center 1 through the internal network. In this way, the services in both of the data centers are not overloaded. Okay, so above is automatic network failure detection system and automatic traffic scheduling system we designed to handle internet connectivity failures. Based on two systems, we can get the following benefits. First, we can automatically handle internet connectivity failures without manual operation. The average recovery delay is less than 5 minutes, and failure detection delay is less than 1 minute. Second, we avoid data center bandwidth congestion. Requests are dispatched to different data centers based on their bandwidth capacity. Third, we use an internal network traffic load balancing system to rebalance traffic based on the backend service capacity. It avoids overloading the backend services caused by the automatic traffic scheduling system. Okay, finally, thank you very much for coming.